Okay, this is a short video about photoelasticity, which is a pretty cool phenomenon to look at, and it also appears on some A-level syllabuses, so I thought I'd give a little bit more information about it. So why talk about photoelasticity? Number one, it just looks cool. I mean, there it is on the right. Number two, it can actually be used apparently for testing structural models. I imagine that in this day and age it's used less and less for this as computer modelling techniques have advanced, but in the past potentially maybe this was more important. And I just wanted to give you a hint that it's different from optical activity, which is another thing that is sometimes on A-level syllabuses, and they kind of work in different ways. So I wanted to give you a hint about that. So the demo that I've got running on the right, which you can see, works like this, and I'll show you the real thing in a minute as well. So I'm using a white LCD screen, a white computer screen, as a source of already polarized light. Then I've got some object in front of it, in this case some yellow jelly that I made yesterday. Then I've got a camera with a Polaroid filter blue tacked, so it's over the lens. And I've rotated the Polaroid so that the LCD screen, even though it's white, appears black. So the polarizing filter is blocking out the light from the LCD screen. And if I switch to this mode, hopefully you can see the actual live setup. So here is my camera, and you can just about see around it, there's this square. I'll get one out of the packet to show you. It's a small square polarizing filter like this that's been blue tacked over the camera. Then I've got my jelly here, and then I've got my white screen here. So this is producing plain polarized light. Then I've got my object, then I've got my webcam with a Polaroid that is blocking out the light that is coming directly from the screen. But the light that goes through the jelly, you can see, does not get blocked out. So this is now being viewed from the webcam in that picture there, the webcam with the Polaroid in front of it. This screen behind here, which appears black, is actually white to my eye, not looking through a polarizing filter, but through the polarizing filter it appears black. But when the light passes through the jelly, you can see it again. So something strange is going on, very strange. All right. And just to show you with a paper background, this is how the jelly looks with a paper background. It just looks like jelly. But when I put and with no Polaroid filter, when I put the LCD screen behind it and the polarizing filter over the camera, then you start to see these cool colors. So what's going on here? How to observe it? Basically, the way I just said it, it's going to work with a transparent solid, like jelly. You need to view it ideally between crossed Polaroids is an easy way to do it, although in this case I don't need two Polaroids since my LCD screen is already polarized. But if you've got an unpolarized light source, then you need to put a Polaroid in front of it. You need to put the object under strain, so you need to deform it. You need to deform the object so that it's under strain, so I can deform this jelly by bending it from side to side or whatever. And you see these coloured bands, and these coloured bands actually indicate areas that are under strain, and I guess the closer together the coloured bands are, the greater the strain is. How can you observe it? What does it work best with? It can work with transparent objects that are already under strain, like moulded plastics. So if I just take the jelly away, try not to drop it, it's stuck to my finger. If I show you a plastic ruler, when I put the plastic ruler between the LCD screen and the webcam, you can see all these coloured bands, which look super cool. That's because the plastic in the ruler is already under strain. Now you might wonder why it's under strain. I'll talk about that in a moment. Okay, but it is. So moulded plastics work well. Solids, transparent solids that can be strained a lot, that can be stretched a lot or compressed a lot, like jelly or silicone sealant. So here I've just got a bit of, if I switch cameras, right there. Here I've got some silicone sealant, the kind of thing that goes around showers or kitchens or whatever. It's just a bit of silicone sealant that came off something that I was trying to make and it didn't stick. The good thing about silicone sealant is that it's very stretchy, so you can put it under a lot of strain. So if I put the silicone sealant in between here and stretch it, you should see it changes colour and you can see coloured bands. It's kind of hard to see actually, it's not working so well today. You can see it a bit there, or if I twist it maybe you might see some different colours. So that's silicone, works all right with that, and then obviously jelly, the thing I had before, is the best, because jelly you can put under a lot of strain, you can deform it a lot, so you can compress it. Oh, this is jelly that, you know, this is just any old jelly. This jelly is actually yellow because it came yellow from the packet. It obviously works better with transparent jelly. I could try putting this under tension. Kind of tricky to do probably without destroying it. Hey, that looks cool, doesn't it? Basically you can have a lot of fun with this. So this is the kind of thing it works best with: jelly, silicone, and things that are already under strain. Why is the ruler already under strain? Well, I don't know, but I'm imagining it's because of the moulding process. When the ruler gets moulded, it's probably injection moulded, which means liquid plastic gets injected into a mould and then it cools and solidifies, but it's not all going to solidify at exactly the same time. So some bits, probably the outside, is going to solidify first and then the inside is going to solidify afterwards. It's going to depend on how the ruler cools basically. And usually when things solidify, when liquids solidify, they contract a bit. So potentially if the outside has already solidified and then the inside solidifies, it's going to contract. There's going to be stress and there's going to be strain. Some bits are going to be stretched, some bits are going to be compressed potentially. So I imagine that's the source of this built-in strain, built-in stress in moulded plastics, is the uneven cooling of it. But that's not I'm not an expert in this, so I'm not stating that as categorical fact. I'm just saying that's probably what's going on, and it's cool to look at with different moulded plastics. The question you're probably asking is, how does it work? Well, what I want to say is it's not the same as the optical activity that you may have learnt about with sugar solution and a polarimeter. So some substances are optically active, by which we mean they can rotate the plane of polarization of light. And this is not the same thing going on here. Okay, it's not just a case of the plane of polarization simply being rotated by something that's optically active. It's because when these transparent solids are strained, they become birefringent, which means they have a different refractive index in different directions, and they have a different refractive index depending on the direction of polarization of light going through them, which is weird. And then it's due to the interference of light that's passed through the object, but experience different refractive indices. It's not, I mean, really a good explanation of this would go beyond A-level physics. It's not something that can be explained easily at A-level level, and it's not really on the syllabus to understand how it works, but it is on the Edexcel syllabus, for example, to know that you can use polarization of light to test structural models, and this is one way you could do it using this experimental setup. So I'll leave it at that. I'll just jiggle the jelly around a bit more because it's kind of cool. And you could think of all sorts of fun things you could do with this. You could put a vibration generator underneath the jelly and actually use this to explore the standing waves that form in the jelly, all the different patterns of standing waves. I've done that before. It's amazing. It's basically a whole lot of fun. It's a shame that the explanation is a little bit tricky to understand how it actually works, but it's a very fun thing to play around with jelly, silicone and moulded plastics. So I hope that's interesting, and maybe you've learnt a little tiny bit about it, but not much. But certainly it's something that's easy to observe as long as you've got an LCD screen and a polarizing filter.